Hi guys, today we are going to continue the discussions of the analysis of plate trusses. Last time, we considered the use of the method of joints in analyzing plate truss, in which we consider the equilibrium of each joint to solve for the member forces. This time, we are going to analyze truss by the second method. We call it the method of sections. Method of section is used when only specified member forces are required, meaning not all the member forces are being asked in the problem. So, again, as usual, the first thing is to solve for the support reactions. So, considering the given external loads. In this case, we have the simple support. A is here, vertical and horizontal, and roller support at B, vertical. Okay, we assume that we know now the values of these support reactions. What we do now is to start the method of section. The first step is to pass an imaginary plane cutting the unknown member forces. Let's say the required member forces are only member CD and CE and AE. So what we did is we are going to draw a line here representing an imaginary plane cutting the beam into two sections, the left and the right portion. So since we cut the beam into two, therefore we expose the member CD here, member CE, and member AE. So we now have the free body diagram. So next thing is to assume the directions of these unknown forces. So let's say for AE, we assume it to be compression towards joint A. And then member CE is also compression. We assume it to be towards this joint C and also CT. So this is the free body diagram of the left portion of the truss. So this is only our concern. So we now go to the equilibrium equations to solve for the unknown member forces. Okay, by inspection, if we are going to start summation of moment at E here, we can solve for the horizontal member CD here. Okay, considering only the vertical reaction at RA. Okay, so our equation will be like this. Summation of moment at A equals to 0. Okay, so no. It should be E. Summation of moment at E equals to 0. So we have RAY here. RAY multiplied by this distance, which is 4, equals CD multiplied by this distance, height as 1 meter. So since RAY is known already from this, so we can see that CD is solved. That is positive. Positive means our assumption for the direction of CD, which is compression, is correct. So we can write this compression. Okay, so one member force is solved. Member CD is solved by taking summation of moment at E. So considering only RAY and CD. Why we did not consider CE and AE? Because these two member forces passes through the reference E here. Okay, next. We can now take summation of moment at C. Here, taking summation of moment at C, which is equal to 0, we can solve for the again, taking summation of moment at C is equal to 0, we can solve for AE considering RAY and this RAX. Okay, let's write the equation. So here, we write summation of moment at C equals to 0. So we have RAY multiplied by half of 4 here, that is 2. Okay, here, plus AE multiplied by 1 minus RAX multiplied by 1 equals to 0. So since RAX are solved, RAY is already solved here. AE, we can solve for AE. AE to be 2RAY plus RAX. Okay. So we can solve for AE. AE is equal to RAX minus 2RAY. Okay. So if AE is positive, that means the direction of AE or the assumed direction of AE is compression is correct. If it's negative, therefore it is tension. Okay? So we are done with the member force CD and member force AE. We can now solve for CE here. Okay? CE can be solved by taking summation of moment at A, but we only consider the vertical component of CE here. So this one. So if we are going to take summation of moment at A here, we can solve for CE by considering the vertical component of CE. If we are going to solve for CE, we can also use summation of forces. Summation of forces vertical equals 0 using the vertical component. Summation of forces X is equal to 0 using the horizontal component. And summation of moment at A equals to 0 considering the vertical component only. So whichever equation you want to use, then there's no problem with that. As long as we have these values, correct values for the previous member CD and AD. So our equation, if you're going to use for summation of forces vertical, for equation will be like this. Summation of forces vertical y equals 0. We consider RAY and this CE vertical component. The vertical component is 1, this is 2, then square root of 5. 1 over square root of 5. If we are going to use summation of forces X equals 0, then our equation will involve RAX, AE, CD, and CA horizontal component 2 over square root of 5. Okay? So, that is the outline of the method of sections. Again, what we did is, we use the method of sections if only specified members will be determined. So, in this case, we are required to solve for the member forces CD, CE, and AE. What we did is, we pass an imaginary plane cutting through these members. Then consider the left portion, drawing the free body diagram of the left portion. Then assuming directions for the unknown member forces, whether it is tension or compression. And then start with taking summation of moment at the joint wherein you can solve for any member forces, unknown member forces. So in this case, we take summation of moment at E, solving for CD. Then we take summation of moment at C, solving for AE here. And then we have three options to solve for the last member CE. Take summation of forces vertical equals to 0. Then consider the vertical component of CE. Taking summation of forces horizontal equals 0, then consider only the horizontal component of C. And also, summation of moment at A equals 0 here, you consider the vertical component of CE plus the other external forces. So that's how we analyze the plate trusses using the method of sections.